All right, so we're looking at introducing some ideas of integration here. It would be helpful if you go and watch the previous video on what's called the left endpoint estimates. So if we wanted to determine the area under a curve, such as this f of x, we can take rectangles of whatever width we like, but in the previous video we did rectangles of width 1, so you can see that the width of these rectangles is 1. And then we made a rectangle using the left endpoint. So this point here would be 0, f of 0. Here would be 1, f of 1. And then basically you make rectangles out of it of width 1. But you can see, as we spoke about before, that this is an overestimate of the area under the curve. So a left endpoint estimate will be a overestimation of the area under the curve for a decreasing graph, f of x. But you can imagine if we made those rectangles smaller and smaller, we would get better estimates. So let's look at what that might look like if we were to make the rectangles half the width. Okay, and obviously we're missing some rectangles in the middle. So if we put some rectangles in between, you can see now that the error has decreased. We're not overestimating by as much. Okay, so you could consider the fact that if we made them essentially infinitely small, we made those rectangles infinitely small with infinitely small width, that we could begin to get a very good approximation. In fact, we can get the exact area under the curve. So if we just delete these, we can show you what the area under the curve would look like exactly. So you can see that if we were to estimate the area under the curve, so you can see if we made rectangles of infinitely small width, we could get a very good approximation for the area under the curve. And that's what this blue shaded region represents. It's the area under the curve between, in this case, between 0 and 6. Okay, and so what I just wanted to do in this video is introduce this new terminology, which is what's called an integrand. And so if I show you what that looks like, we can say that the area under the curve is what we call the integral between some point A and some point B. So in our case, A would have been 0 and B would have been 6. And the integral. So, and the reason it looks like this is that it's like a long S. So it's what's called, one way to think about it is it's the sum of an infinitely small rectangles between A and B, the sum of the area of infinitely small rectangles between A and B underneath the curve f of x. And then we write dx at the end to say that we're taking the antiderivative with respect to x. So we'll talk more about why exactly this is the case and relate it to derivatives in another video. But this is the notation we use to represent the area under a curve between some point A and some point B. So hopefully you can just wrap your head around that idea of making rectangles smaller and smaller until you can get an exact area under some curve.